Hi, I'm Ken. Can you hear me? Okay, looks like I can be heard. Should I give everyone just a couple of minutes maybe to get a drink of water? Um, while that's happening, if you want to step away for a moment, I'll just give everyone a couple minutes. If you would in the chat, it'd be really helpful if you could just type in some of the languages that you know. So I'll be talking specifically about some things having to do with Python, but maybe you've learned some JavaScript or C, maybe you know R or Java, C++. So it'd be interesting to know the other kinds of languages that you've worked with. Good. I see R in JavaScript, a lot of R, which is definitely what I would expect. SQL is great. Thank you for putting that. MATLAB, fantastic. Cool.
Ken, sorry, could you make
Yeah,
me host real quick so I can help you? I
sure.
can start the recording and stuff.
Yeah, how do I do that?
You just have to go to participants and
Uh-huh.
on my name that says helper first.
Got it.
Say,
See it.
yeah,
Yes.
there you go.
Thank you.
All right, perfect. I'm gonna start the recording now, and if you need anything, I think I'm the only helper for this session, so
Okay, well, thank you so much for your help.
of course.
No, you're not. I'm
Okay,
here. Sorry.
Oh, perfect. Hi, Sebastian.
okay, so I guess I'll get started here. I'll be going slowly at first, so hopefully it won't go too fast. I also want to be sharing my screen, so let me see how to do that. I use so many different things. It's hard to remember how to do this. Yeah, there we go. Share screen, the big green button. Whoops, it says you have disabled screen sharing. Maybe you have to make me host again.
Now you should be able.
Yeah, now you're co-host, so you should be able to do everything. But if you leave,
Oh no.
you know, nothing will break down.
Let's see. It's actually okay. I'm having to do some silly things with system preferences. I'm gonna have to leave apparently and come back to enable screen. Let me just.
All right, that was sudden. Hold on tight.
Okay, let me try to share my screen again. Great. Here we are. So what I'm going to be talking about today is, oh, hey, Julian, I see you. I'm going to be talking about how to use some of the latest features in Python to help you write better code, and also a number of tools that exist out there that include linters and type checkers. And if you come from a language that has static types like C or Java, some of this is going to be familiar to you. If you have only used languages that are dynamically typed, like Perl, Python, JavaScript, and R, some of this is going to be rather new. But hopefully you'll quickly see the advantage of using these kinds of ideas. I wanted to go over a little bit on the page for this, just to cover a few things. I did put a lot of stuff up about how to set up your environment. And unfortunately, I won't be able to step through all that, but it's pretty well laid out in this new book that I've written. It's called Mastering Python for Bioinformatics. And I'm going to be using that text. And you have complete access to this for free through the U of A library. So if you can go to this link here, and if you search for that title, it will come up with an electronic version that's available through O'Reilly's Safari platform. So I encourage you to open that up, and I'll just be starting in the preface this morning and hopefully getting through part of chapter 1. That's my goal for today. And the ultimate goal is to write a program that will solve the first problem from this website called Rosalind.info. Rosalind Franklin, of course, should have received a Nobel Prize for her work on DNA crystallography, but she didn't. She died young. And let me just log in here with, so the Rosalind, but she did get this website named after her, so it's all the same, right? And on the Rosalind website, okay, all this, it's a number of bioinformatics challenges. They're very popular for learning bioinformatics, and it introduces a lot of the kinds of ideas that we use a lot in bioinformatics. And so mostly what I'm going to be showing is how to write a command line program. So you could solve this, in any language whatsoever. There's nothing about Rosalind that asks you to use Python or any particular language. And you could put in the data however you like. But I'm specifically going to show you how to write with Python a command line program that documents and validates its arguments, and then has tests to verify that it actually works correctly, so that you can then learn how to do things called refactoring. So, the challenge is, given this any string of DNA, count how many A's, C's, G's, and T's that you find. So ultimately, that's what we're going to be trying to do. And all of this is covered in, that's the entire first chapter, is how to write this. If you're on a Windows platform, you're pretty much going to have to install Windows Subsystem for Linux, which seems like a very high bar. You basically have to learn a new operating system in order to write command line programs. But it's just a fact. I have a Windows laptop. It is utterly worthless for this kind of programming. So I have installed WSL. I use version 1 because of the security requirements of mine, but WSL2 it's a preferred version. So however you have to do that, it works. And Apple users, you can just open a terminal. The native terminal application is just fine. I use iTerm too, but it doesn't really matter. And of course, if you're on Linux, probably all of this is old hat to you. I will be showing you how to use a code editor called VS Code. It's quite good. A lot of people like these kinds of integrated development environments. They're called IDEs. I tend to just write in a terminal using the Vim editor and running things on the command line. But if you're more comfortable in an IDE, you should absolutely use it. They can incorporate a lot of helpful hints and menu options, so that things aren't quite so scary when you're writing a program. All the source code is in this GitHub directory. If I go to that, if you're familiar,
sorry to interrupt. We
yes,
have
go
a
ahead.
question in the chat. Why wouldn't Git Bash work for something like this?
It might on Windows, but it's Git Bash is just like only implements a little bit of the command line. So you could use it, for instance, to check out the GitHub repository, but I don't think that it's going to like really respect your environment and help you install Python and all the things that you would need to do. Actually, is it possible for me to see the chat in addition to?
Should be, yes.
You should be able to, in the screen sharing bar you have somewhere, click chat.
You are screen sharing.
There should be a chat somewhere, or oh no, it's in the 3 dots on the far right, I believe.
Okay.
It's all from memory.
Yeah,
thanks, Jen. Same.
I see the 3 dots, and I see record, show subtitle, reactions. I don't see something.
Doesn't say chat.
I just don't see it. But I'm old, so
maybe right next to the share screen button.
I think it's different when you're actually sharing the screen.
Yeah. Well, I guess if you would just alert me to those kinds of chat questions, I would really appreciate it. I'm just looking at these other options. Oh well. So if you're familiar with GitHub, you can click on this code button here, and then you can highlight probably this URL to clone this. And all of this is covered also in the preface. But I show here, like for instance, in your home directory, I might suggest you create something called work or Python or something like that. And then you could clone this into that directory. And now you should have a directory like this. And that's going to be useful because I have provided a lot of tests and data for you to work with for all of this. It's possible that you already have Python installed. If it's version 3.8.6, that's okay. That's a pretty good version. The latest version out right now is like, actually, is it 3.9.5? It's something like that. It is good to know how to download and install Python from source. So I would recommend ultimately that you do that. But if you already have a version of Python, it should be fine. There are a number of requirements for all the code, and inside the root directory of this is a file called requirements.txt. It's a very common way to indicate modules that need to be installed. And so I didn't indicate any versions of this. I just, whatever's the latest version is probably just fine. So all of these modules need to be installed in order to do ultimately all the exercises. For instance, I definitely am going to be showing you about PyLint, which is a linter which finds problems with your code. Another one called Flake8, which is in here. It's just another kind of linter. And I'm also going to be showing you a tool called MyPy, which checks for how you use types. And then there are ways to test your program using PyTest. And then there are some integrations for those tools to be used within PyTest. So, and don't worry, I'll show you what all this means here as we're working through it. So, oh, maybe I should have introduced myself at the beginning. My name is Ken Youens-Clark. I have been a senior scientific programmer at the University of Arizona. Last fall, I joined the Critical Path Institute as a data engineer, but I still do some part-time work for the U of A. Also, I will hopefully be teaching a class this fall, Biosystems Analytics, which is course BE 434. I've taught that before, but this time I'll actually be the teacher of record. So if you are interested in this and would like to spend a whole semester learning how to write better and cleaner Python, you're welcome to join me. So that's kind of the intro here. All right, let me get back to. Okay, so I'm going to start off by showing you a simple program. Let me make that much bigger to kind of get at some of what I'm talking about. This is a program that I just wrote. It's a very simple command line program. It asks for your name, and then it's going to print hello to your name. So let me show you how that works. If I run this type check, it's going to say, what is your name? And I'm going to say Ken, and it's going to say, hello, Ken. So a few things to note here. When I write a command line program, it's typical for me to use something called the shebang line here. So in Bash, this is essentially, it kind of starts off like a shell script. And in Bash, the % or the hash sign is a comment. And this is a special comment. It's followed by an exclamation point, which is often called bang because it's a lot shorter to say. So we colloquially call that shebang. So the shebang line tells the shell to run the environment and find Python 3. So there could be a number of Pythons installed on your system, and I'm telling it to just find the one that the environment finds and use that to execute the rest of this program. So that's what's going on this line. And then I'm using the input function to get your name. This is the prompt that is put to the screen, and then the result is put into the name. And that's going to be a string. Everything that comes from the input line is a string. And then I can print this using an F string, which I'll talk about in a minute. And I can interpolate this variable inside here by putting it in squiggly brackets. So it runs, and hopefully everyone understands that. If I do something completely silly, like try to divide the string by 2, that's just an illegal operation. And so the question I would have for you, and maybe you could monitor the chat, I would ask you, especially if you're not familiar with Python, what would your expectation be of this program? Should it even compile? Should it even run? Or will it run and then ask me my name and then blow up? So who thinks it will run? It won't even compile. Who thinks that this is just wrong and it won't even compile? I see one hand. Okay, you're wrong. It unfortunately will run. It will ask for your name, and then at the moment when it says, hello, when it tries to print that, it's going to blow up because it's going to try to divide the name by 2. So let me run this, and I'll put in my name, and you see it ran. It asked me for my name, and then it blew up at runtime. So we call that a runtime exception because it created an exception. The exception right here is a type error. If you're not familiar with exceptions, you wouldn't know that that's an exception, but in Python, that's what's happening. And it's telling me exactly what the problem is. I'm trying to mix strings and integers in a numeric operation that's just not going to work. Unfortunately, it would seem like that's information that Python would have before it even starts to try to run. Like the first thing it has to do is read the whole program top to bottom and make sure that it's actually valid syntax. Well, this is valid syntax, it's just not valid code. And so you would kind of hope that maybe it would stop you, it would prevent you from doing this, because this is an extremely simple program. It has 2 lines of code and there's 1 bug. What happens when there's 500 lines of code or 5,000? There's lots of potential bugs waiting in there. And so if you're coming from a statically typed background like C or Java, you would know intuitively, well, if I say something's a string, then I can't use it in a numeric operation like that. And so we have these tools called linters that will help find things, find problems with our code. And I said, one of them is called pylint. And I can run pylint on this program. And the most that it has to complain about is that I haven't put a doc string here. And so a doc string, if I was going to make this happy, it would just be basically a bit of documentation like do something stupid. And that is enough for it to be a doc string. It's basically just a string that documents what this program does. And once I've done that, now pylint is happy. It's like, yeah, I can't see anything else wrong with your code. 10 of 10, you're doing great. So there's another one that we have called Flake 8, and I'll run that on here. And the fact that it has nothing to say at all means that, again, it finds no problems with this. But there's another tool out there that's been introduced in the last few years. It's called MyPy. And if I run that on this program, it actually finds the type error. So it says here on line 6, you're doing something that you shouldn't do. Now, this is happening without my running the program. This is called a static checker. So it's actually just looking at the source code and finding that there's a problem. And if I go here to line 6, sure enough, there's the problem. And so if I get rid of that and go back and run MyPy, bam, no issues. So this is something that's new to Python, the addition of type hints, and I can actually put in here a type hint, and it looks like it does in other languages. It's a colon followed by the type. So the str type in Python is a string. So if I say name is a string, then I'm actually annotating it in the source code. And sometimes a lot of times you need to do that for MyPy because it can't figure out what the type of a variable is going to be. So as your Python programs get longer and longer, it becomes more and more necessary to run these kinds of linters and type checkers, and to also incorporate types into your program so that you can get this kind of checking. Okay, so with that, that's kind of an overview of a bit, the TLDR here of what I'm going to be going over. Are there any questions so far? I'm going to drink a bit of water. Okay, I guess do I have to stop sharing in order to look at the chat? I'm just gonna look at the chat. Okay, so no problems here so far? Okay, go back to squaring. Okay, so I'm gonna close this. I'm gonna reference the book now. I'm going to go back here to a few things. Hopefully you're able to just read along with with you could pull it up in your web browser, and it's all the same content, all the same text. And so I'm just going to go over a few things. Here I note that since Python 3.6, you can add these type hints. So if you have anything older than 3.8, really, you should upgrade. And I talk about using PyTest, PyLint, Flake8, and another one I'm going to introduce here is argparse, which is basically how we can document the parameters to our program. And so I talk a bit here about object-oriented programming and why I'm categorically opposed to it, and why I even avoid exceptions. I tend to try to stress a purely functional approach, and if that doesn't make any sense to you, I think it would after you read a lot more of my code. I've introduced here the Roslyn website and exactly what its background is here, there are dozens and dozens, maybe even hundreds of problems to solve there. And I only take the first 14, or not even the first, but I take 14 of the earlier programs just to kind of, because they demonstrate a lot of things that we encounter a lot in Python, in bioinformatics programming. I've only been actually programming in Python for a few years. I spent most of my time learning bioinformatics using Perl and doing a lot of web development. I started with Perl around 1998 and really used it for about 15 or so years. And so in the Perl community, there's this mantra is there's more than one way to do it. And that's actually very frustrating for a lot of people about Perl. Python sort of has the exact opposite approach, which is that there should be just one way to do things and it should be obvious. And that doesn't always work out. There actually are many ways to do things in Python, and I'd like to show you hopefully how many different ways we can count the nucleotides in a string of DNA. So I kind of take a different approach to coding Python. One of the things that I really try to drive home is this idea of test-driven development. So you should actually write tests. It doesn't necessarily matter if you write them first or you write them after. The point of this book and this material is that they have already been written. They've been written for you. They do exist first. And that is technically the way that you're supposed to use test-driven development. But in practice, as you're developing something organically, you don't necessarily know how it's going to work. So maybe you get to a point, your program does something, you're like, okay, I need to make sure it always does this thing, so I'll write a test for it. And I'm going to show you just how simple those tests can be. But the idea of test-driven development is this. You create a test, you run your code, and you verify that your program actually fails. Like it does not do this thing that the test says it should do. Then you write the code that passes the test. Then you run the test and you verify now it does do the thing it's supposed to do. And then now that the program works and does something like, okay, now it actually counts the nucleotides, now you have the ability to refactor your code. So refactoring is basically finding a better way to do the thing. So maybe your program works, but it's dog slow. So now you need to speed it up. But once it passes the test and you know that it's possible to pass the test, then you have some baseline to always go back to. It doesn't matter if it works faster if it gets the wrong answer. It still has to be correct, but you have the freedom to play with it now. And basically test-driven development is just this over and over and over again. Every time you want to write a new feature for your program, you add a test, you add the feature, the cycle repeats. I have some information here about using the command line and installing Python. It's very important. And then a little bit there more about checking out the code with GitHub and how you can even fork the repository if you'd like to basically make a copy of the repository and work in it yourself, and a few other things there. Here's the bit about installing the modules that you'll need. There's a couple different ways that you can install them. I often use this incantation, but sometimes you might use pip3. It just depends, especially if you're on like a Windows platform, that might be better. And some things here about these initialization files for PyLint and MyPy that could be important for later programs that we write. So one of the things that I have done for years now with my students is I think it's important to not start from a blank page. So if you're trying to, and actually I saw Hadley Wickham talk when he came a couple years ago to talk about R and RStudio, and he pointed out the difference between using a statistics program like JMP, which is very menu driven. So you want to do something, you can probably find the menu option to help you stub out that code or write that analysis, and how different that is from R, which just presents you with the prompt to start writing code, and that's very intimidating. I mean, you basically have to know what you're going to write before you write it. And I think that's a very difficult way to get started. So I wrote this program called NewPy that helps you create a new Python program, and you can install it using pip from the command line. And once you install it, you get this program called NewPy. And if I go here on my computer, I'll just go into my home directory for a moment, and I'll say NewPy, and I'll call it RB 2021. And bam, it just created a program for me. So it's basically two steps. You have to run this to install NewPy. And once that runs, actually, I can just paste it in here. It probably won't do anything yet because it's already been installed. And so once you do that, now you can run NewPy. And if you run NewPy without any arguments, it will actually tell you how it's supposed to be used. And if you'll notice, the very first word here is usage. So it's typical to call this the usage statement. And what I want to show you is how you can create a program that also creates a usage statement that says, oh, you didn't give me the right arguments. You need to give me this in order for me to run. And I can also run NewPy with -- help. And it will present a longer version of this, or -h. So this is very, very common in command line based programs. It's pretty much universally expected that your program will respond to -h and -- help flags with something like a usage, and so that's what we have here. So with this, we're going to use this program to create this new another program that is going to be called DNA.py that's going to count the nucleotides. And actually, I lied here. I meant to be showing you all this from within VS Code, because probably this is more friendly to you. And I want to make sure that I'm not acting like an old man here who's only been using the command line for 25 years. So here I am inside VS Code, which is, I shudder to say, is a Microsoft product. I come from in the mid to late 90s when Microsoft just had nothing but enmity for Linux, and I was getting into open source programming. I really came to just detest Microsoft, but I have to tip my hat to them. VS Code is actually a really a usable piece of software, unlike Outlook. And this is actually a pretty pleasant way to write code. And so here I am inside the source code that I checked out from GitHub, and I'm in the O1 DNA directory. And if I do an ls, which is file listing, there is actually a DNA in there right now from my having solved it earlier. I'm going to get rid of it. And if I ls, I'll see there's a bunch of solutions there already. And if you want, you can run solution one. And so I'm running it by saying // which is Gesundheit. I'm running it by doing // which dot is the current directory, and then / is the directory separator. So I'm saying run the solution one iter.py that's in this directory. And because of the shebang line that I mentioned earlier, it's finding that this is a Python 3 program and then running the rest of the program with Python 3. And if I run this, I see that just like NewPy, without giving this any arguments, it's saying, hey, you need to give me an argument. It's required, and it's called DNA. I'm like, okay, well, let me just give it AAAA. And if I do that, it's going to print 5000. So the 5 is how many A's it found, and then the C's are in the second spot, G's are in the third, and T's are in the fourth. So it found 5 A's and nothing of anything else. And so we're going to look at how to do that. But the first thing is, how do we write a program that just does this part, that just validates the command line arguments? Because this is honestly one of the most crucial things that you need to get right when you're writing command line programs. It's very common in bioinformatics to build enormous pipelines. The previous speaker was talking about working on HPCs. That's a very important part of when you get into large data analyses. You might have hundreds of sequence files that you need to analyze. And maybe some of them, a good percentage of them might be corrupted. They didn't make the trip from the sequencing facility to your HPC, or just a disk got corrupted, and somewhere along the way, some portion of your data is bad. And if you're not validating the input files and then loudly failing when you can't do something, then you might just run the whole analysis and get spurious results because you didn't use all of your data. And at no point did the programs in the middle ever say, stop, I got something unusable here. You need to fix this before I can go forward. So I'm going to show you how to do that. So I'm going to say new PY, DNA.py. That's the name of the program that I want to create. And when I do that, it says done. And I just created a new PY. A new program called DNA.py, and it shows up here. And if I open it with my text editor, you'll see it has a lot of code already written, about 85 lines of code that was written for you. And so, let's run it now and see what happens. It gives me this usage, and it says, okay, right now this program accepts something -A, -I something, -F something, -O, and then also str. And so just a little bit of information here about this usage that we're looking at. The arguments that are in square brackets, that is a meta, like a meta character is telling you that these are optional arguments. So they're options. Some of them take a value.
Can I just interrupt you quickly? The chat asked if you can go to full screen, that people can see better.
Okay.
Thank you.
Is that better? I can also just try to make the text larger.
Yeah, better. Thanks.
Thank you. So the arguments that are in square brackets are optional. Some of them take values. Some of them don't. The -O flag just stands by itself. So that's called a flag. But this one says it takes a file. And then at the end, it just says str, which means it takes some sort of a string. So let's look at the code that creates that. I'm going to go to the bottom here because oddly, this is kind of how Python works. Python reads the entire file top to bottom. And if you just start writing Python code like the one that I showed you to start off with, it didn't have any of all this extra stuff. It just had a couple lines of Python just right there in the main body. And so when Python read those, it just executed them. Here, I've created more structure. I've created a couple functions. And the program is going to start in this function called main. And if you come from C and Java, that probably feels like home to you. If you've only ever written in R, you may be curious why main. In programs that have a heritage from C, there needs to be a main module, and in that main module there needs to be a main function. That is just where the program starts, always and forever. Amen. So I like to mimic that with Python. I just feel more comfortable starting in main. But if I don't tell Python to actually go execute main, it will never do that. So this program is read top to bottom by Python. And when it gets to these last two lines, when the program is being executed, the name _name _, that is a special variable inside Python that will be set to this string _main _. They're often called dunders for _. It's something that I kind of detest about Python, but this is simply the way it works. So that's what this last two lines do. They look to see if this module is being executed as a program from the command line. So that's what's going on. So what's going to happen is that the program starts in main. And I've added type annotations. So if you've never seen this in Python before, this is what it looks like to say, to define the arguments and the return type of a function. So this main never takes arguments. So if there were arguments, they would go here inside the parentheses. And this main doesn't return any value. So I'm using the special value none to say that nothing will come back from this. And the first thing I always do is call get args. And this seems like I hope it doesn't seem like just beating you over the head with this, but this is how to create a well-structured Python program that validates its command line arguments. So this may seem a bit tedious. I hope not too much, but this is really necessary, and hopefully I'm going to show you why. So getargs is going to be called, and then it's going to have all these arguments that have been defined inside getargs. So let's look at getargs. This is using a module called argparse, and there's a lot of documentation that you can find on argparse. In order to use it, I need to import it at the top of the program. The imports don't have to be at the top, but it's good style. And you remember when I was running pylint on that first program and it said there's no doc string, you'll notice here up at the top is a doc string. Okay, there we go. So at the top of this is the same shebang line that I talked about in that one simple, what is your name program. It's trying to execute Python 3. It put here a doc string is simply a string. You notice it's not being assigned to anything. It's just a string that exists literally inside the program. And I'm using Python's triple quotes to allow me to use new lines inside of it. And so I can put whatever data I want here. It's just strings, and it's actually completely ignored by Python. I think it's good form to put your name and the date, your email address in case someone has a problem. Like if you're writing this program for someone else in your lab, it's important for others to know who wrote this. And actually it can be really useful to know when you wrote something, because you'd be like, wow, a lot of time has passed. So that's a doc string up at the top. It's very typical to put all of your import statements together at the top of the program. It's not a requirement. It just is nice. And I'm going to talk about this typing stuff in just a moment. But that's a new module that has existed for the last few years that allows me to describe the type of data. So I'm going to be using argparse to create this argument parser. And this is a lot of text to try to remember. That's why I don't want you to ever try to remember it. I think you should use newpy to just stick this in there, boilerplate for you. And then all you need to do is go in and alter these things. In the parlance of command line programs, there are different types of arguments. This one here is a positional argument because its meaning is derived from its position on the command line. There's a very useful program or command called chmod, and if I don't run it with any arguments, it tells me that in its own way, which is not extremely helpful, that it requires two arguments. One is the mode, like something like 755, and then the other thing is the entry of the file. And if I get those things mixed up, it's not going to work. So if I were to try to chmod my DNA program to 755 or 755, that's not going to work because I got the positional arguments in the wrong order. The mode has to come first, and then the name of the program to, the name of the file or the directory to apply that to. So that's a positional argument. But chmod also has all of these options. Like, for instance, if I wanted to change all of the programs recursively going down through this directory, I could use -r. So that's a flag. A flag is something that's either present or not. So when -r is present, it says do this thing recursively. When it's not present, it's just don't do that. And so that is this is the Boolean flag that I define here. That's a flag. So this is how you would, if you wanted something like that in your program that's either on or off, this is how you define that. It's also possible to have arguments that are named, but they're options. So it could be there, and if it's there, it should be this value. So if you wanted to do something like that was a string value, like you were creating a program to that greeting program. Like, let's say instead of it asking you using the input, it was going to expect that your name was a command line argument, and maybe also the greeting could be an optional argument. So instead of saying hello Ken, it could say greetings Ken, and so the greetings could be an optional argument, but it takes a value. And so that's how you define, here's how you would define one that takes a string value. If you wanted actually that value to be an integer, you could actually put the type here as int. And let me show you what happens here. So all of these have been defined in our program. Let me show you. If I try to give an integer value that is, foo, and I have to give it some other positional argument for this to work, notice what it does for me. It says that's an invalid integer value, foo. So it rejected it. And I didn't write that code. ArcParse did. So I'm getting all this kind of checking for free. I can run this program without that argument because it's optional. And you notice here when I run it without any, I have to give this positional argument that's required. But notice that the integer argument has a default value of 0 because I indicated that here. The default value is 0. And likewise, if I wanted to change the default value for this -a flag, I could, make this be, cookie. And if I run this again, you'll see that the string argument has a default value of cookie now. So this is a really convenient way of creating a command line interface for your program that can set reasonable defaults and also validate the data that's coming in so that people aren't allowed to give you, a bad integer value. Are there any questions about this for a moment? So one of the reason why this is important is because the goal is to create a program that you can change the behavior of the program without changing the code. So if you're used to writing, say, an R program or maybe a Jupyter notebook, and you have an input file that you want to work on, you're probably used to changing some line in your code that says, input file is this directory name. And then when you get a new set of data, you change it to a new directory name or a new file name, and then you run it on that. The point of this is that we should not change our code in order to change that kind of behavior. That's a parameter to the program. We should just be able to give it from the command line, go process this file or go process these 500 files, and it should be able to take care of that for us. And likewise, so if we're going to accept these things as command line parameters, we also need to be able to validate that they're good. So I've showed you here, -i, foo. It also will reject anything like 3.4 because that's not an integer. So let's say that you were trying to you wanted a flag that was like a p-value, and you wanted that to be a float. Like I can change this to be float, which is a type in Python, and I'll call this float, and maybe I'll change this to -p, and I'll change this to p-value. I'm going to save that, and if I run the program and ask for the help, you see now that my flag has been changed to a floating point, and the name has been changed. It defaults to 0. And now if I run this, actually I have to change this code down here. I'm going to change this to p-value. So if I want to print the p-value, it's going to be available to me in the args.p-value, and I'll change this here, p-value. So let me run this now with a p-value of say 0.4, and it still requires some sort of a command line. Uh-oh, has no int. What did I do wrong? Oh, well, let's see, it's saying line 61. So let me find that. Oh, right. P-value. Okay. So now I have to talk about this args structure. So what you saw there was that I was trying to update my code, and I missed a spot. I was trying to reference a field that didn't exist. And the reason is because I created a type to represent the arguments to my program. And so now let's go back and talk about this bit here. I created this class called args. And I said at the beginning that I pretty much detest object-oriented programming. But here I am creating a class. And I'm using this class as essentially like a struct from C, if you're familiar with that. I'm sure Java has something similar. And the only thing that I would say that you need to know about objects is that they can inherit from each other. So it's very much like a taxonomy, like we have mammals, and then mammals, the subclass of that is primates. So primates have all the things that mammals have, right? I hope I said that right. Anyway, so and so here we're saying that args inherits from this thing called named tuples. So now I have to talk about what named tuples are. And for that, I'd like to go back to this a little bit. going to start here. Here we are in the first chapter, and I'm going into a little bit of the things that I've showed you, like how this program works right now. And I haven't showed you PyTest yet, but I start here talking about starting the program with new PY and getting into this. And we saw that about PyLint, so here we are with named tuples. So what I want to talk about for a moment is what is a tuple in Python? Well, Python has these things called lists, and tuples are essentially immutable lists. So let's just talk about lists for a second. So a list is an ordered sequence of items. So let me make this a little bit bigger. Maybe I should make that full screen. Well, okay, that's fine. So a list, I can create a list in Python, and I'm showing here the Python REPL. So REPL stands for REPL, which stands for read, evaluate, print, loop, and that's the bit here that I'm talking about, using the interactive interpreter. So in VS Code, let me show you how I can do this. Whoops, not that. There it is. I can let's see. I think debug console is what it. Let me see. I tell you what, I'm just going to use iterm because I'm more familiar with it. So here in iterm, if you type Python 3 all by itself, you should get something like this, just an interactive interpreter that is a little similar to in RStudio. You can just start up R, and you can just type in commands in R and create data structures and then look at them and evaluate them. So this is very much the same kind of a thing. It's just a console for entering Python code. And so, if you say, if you just put in text, obviously that's not valid Python. So at the moment that you hit enter, Python tries to parse it into Python, and if it can't, then it just throws its hands up, and here's a syntax error. So with that, like, I'm creating something called seeks. And in Python, as with many other languages, a variable is created when you assign it a value. So I'm going to create the variable called seeks. Like for instance, if I just say, what is seeks? It's not defined because I haven't created the variable yet. So if I say seeks is equal to, and seeks is going to be short for sequences, is going to be equal to an empty list. So in Python, we can use double brackets to indicate an empty list. And now seeks is something. So if I evaluate seeks by just typing the name and hitting enter, it shows me that it's an empty list. Another way to set that is to use the list function, like that. And they're both going to be the empty list. And there's a function in Python called type, and it will tell me what is the type of a variable. And so I can see here, this is a list, and it doesn't matter how I create it with the square brackets with the list function, it is a list. And so that's a little bit about the REPL. That's important to show because of what I'm trying to show you here is that I'm creating this thing called seeks, and then I can change it. I can append a sequence to it by, and that will add one sequence to the end. And now a sequence has one value and it's ACT. There's also a function in there called extend. And it takes a list and basically puts the contents of that list on the end of this. And so now seeks has 3 values. Something to know is that in Python, you can alter the elements in a list. And in Python, unfortunately, is zero-based indexing. So the first element in seeks is at position index 0. So I can actually mutate that directly inside the list by just setting it to a new value. Whether that's good or bad. Yes, go ahead.
Sorry, could you make the font a bit larger? Somebody asked in the chat.
Yeah.
There you go.
It's let me. So hopefully that's a little better. So I can change the any of the sequences in place. And if you think that's good or bad, depends probably on your background, but it is possible to do that. And so that's just a little bit about lists. So tuples are very much like lists in that they are an ordered sequence of possibly heterogeneous items. So in Python, a list is never required to be all integers or all strings. That you can just be whatever you want to put in there. And again, that could be good or bad. I think it's generally bad, but that's just how Python works. A tuple is exactly the same, except that you can't change it. Once it's been created, no part of it can be changed. So it's a little odd that the way to create a tuple is just to simply put commas in between things. So I can create a tuple here, and I can look at its type and verify that this is a tuple. But syntactically, most people are used to seeing tuples represented with round brackets or parentheses around them. So that's also a tuple. But it's actually the commas in between the elements that make it a tuple, not the brackets, the parentheses, as opposed to a list that requires the brackets. That is what makes it a list. So the thing that sets it apart is just the commas. So now this is a tuple, and if I try to do any of the things that I was just doing, like if I try to append a new tuple to this sequences, that's not going to work because there is no append method. I can't change anything. Once a value has been set in a tuple, it's immutable. So this is actually really useful. And in a lot of languages that have tuples, these are often used to represent structures. So for instance, imagine I have some sort of a sequence structure that has an ID, like, you download some sequences from GenBank, and each one of those sequences has an ID and a sequence. And so I could represent that, for instance, with, they're both strings. So the ID is just this, random mix of numbers and letters that came from some sequencing center. And then the sequence is the second thing, which is some string of DNA. And if it's useful to create that as a named tuple because I don't want that data to ever be accidentally changed in my program. I can create this little helper called a named tuple that allows me to talk about the field. So instead of talking about the 0th field or the first field, I can instead talk about the ID and the sequence, which is a nicer way to talk about that. And I can do that by using this function called named tuple. And I can say that, I will use this name called sequence, and inside it's going to have two fields that are ID and sequence. And so when I use that, I've created this thing called, it's basically a type. I've created a new type, just like we have integer types and float types. I just created a new type inside Python called sequence. And that represents this structure that has two fields, an ID and a sequence. And the point of being able to use it is that in code, I can start to write this now, where I have this sequence one with these values. And this is how I could reference the fields by their positions, but that's really ugly. This actually is a lot nicer to be able to talk about sequence.id. And that if you come from R, this is something that I will never forgive R for, is that they allowed the dot to be used just as part of a variable name. And it's such an important piece of punctuation. I can't believe they let it go. But in most every other language, the dot allows you to basically call a method on an object. So I'm referencing the seek ID. Whoops, I did not want that. I'm referencing the seek1 object, and then the ID field that belongs to it. And using that, I can create this string. That's a lot nicer and it looks prettier. And actually, it's a lot easier to check this kind of code. But I can go a little bit further by using this module called name typing, and in it has something called a name tuple. And I can create that same structure, but I can describe it now using type. So I can say that there's an ID that has a type string, and there's what I was showing you from earlier, that the way to use the way to create the type annotation is to put a colon and then the type from Python. And this type can be types that you create too, which makes it really, really powerful. So I'm saying that there's going to be this structure called a sequence that has these two fields of these two types. And boy, this seems like, that's going to be really useful. And boy, I do not like the way that is. Let me see. Okay, so I have these types, trying to go through here, and I can still instantiate them the same way. But here's the problem. So let's say I try to create a sequence here, and I say the sequence is going to be equal to 3.14. And so you would think that Python would say, well, no, that you told me that needs to be a string, and so I won't do that. But no, Python will just go right ahead and create that for you. And sequence is 3.14, and I can verify that the type of that sequence is a float in violation of the thing that I told it that I wanted it to be. So you're like, well, then how does that help me? Well, it doesn't help us in the REPL. But if I add this kind of information to my program, then it starts to become very helpful because I can use MyPy to check these kinds of things. So I told you all that so I can go back to my code and look at the mistake that I made. So I created this class to represent the arguments to my program. And I said, well, there's a positional, there's something called positional, there's something called string, there's something called int arg, there's something called file. And I described it with these different types. And so down here, I changed this thing to p-value. And then I went down here and I changed the int arg to p-value. But then when I tried to run it, you saw that it said that there is no attribute int. And it told me line 61. And then I was like, well, what's going on, line 61? Because I hadn't changed that to be the name of this. And so here I'm trying to instantiate my args using the arguments that I've been given. But here I need to change this to p-value. And that is of a type float. So as I'm changing my program, I'm updating the arguments, and then I get type checking. And so let me go back and run this. And now my program works correctly. And if I were to try to, give, anything that's, not that, it's going to say invalid float value. Okay. I'm going to pause for just a moment. Are there any questions? I'm going to drink some water. If the helpers would let me know if there are any questions.
Yeah, no questions in the chat that I can see.
Okay. So I'm going to modify this program now to be what the actual DNA program needs to be. There's only one argument we need, and it's going to be the positional one, but positional is just not a good name. It's going to be DNA. That's the argument that we're being given, and it is a string. And so the only thing I need to do here, the only value I need is DNA. And that's going to be what I call it here is going to be the way that I access the value from argparse. So I'm going to change the metavar from str, which is not very informative, to DNA, and I'll update the help, and I'll say, input DNA sequence. I don't need any of the other arguments. One other thing, actually, I meant to mention here. Don't really have time to cover this, but this type of a file type, argparse will validate files. So if you try to give an argument that's not actually a file, and specifically here I'm saying it has to be a readable text file. That's what R is for, readable, and T is for text. So if I were to, for instance, give it a file that I don't have permission to read, argparse would stop and say, nope, I can't read that file, it's invalid. And that's really important because you want to validate those kinds of things right away and not wait for some program, function deep inside the bowels of your program to try to open the file and then fall over. You need to validate these kinds of things immediately. So I don't need these arguments. I'm going to get rid of them. Don't need that p-value or this. So the only thing I'm going to do is parse the arguments, and I'm going to return DNA. And just to get started, I'm going to get rid of all of this. And I'm going to print args.dna. Let me verify that this runs. I want that to get out of the way. Okay. I'm going to verify this runs. It does compile. And if I run it without any arguments, it tells me that one argument is required. It's DNA. if I give it some DNA, like, ACGT or GT, it prints that. And let's say I give it two values. That's not allowed either. So when I gave it 0 arguments, 0 positional arguments, it didn't allow me to run because it needs 1. When I gave it 1, it ran. When I gave it 2, it did not run because it said, wait, I don't know what to do with this other argument that you gave me. For instance, I could also say dash P is 4.2. Again, it's going to be like, great, but I don't know what dash P means. That's illegal. And so in this way, with actually writing very little code, I've created a fairly rigorous interface to my program that's only going to allow in 1 argument. Now, of course, it could be, it could be garbage. Actually, I can't use. Sorry, I'm used to my command line. I can't use. I can input that. There's no verifying that it's actually valid DNA up to this point, but it does have to be a single string that my program gets. I hope that I'm not just like beating a dead horse here, but I hope that you can really see the value to this. Most scientific programs don't even rise to this level of like verifying that their arguments are correct. So does hopefully everyone see the utility in creating a program with this kind of structure? Okay. All right. So now let's talk about like how could you count the bits in a program? So that's what's going on here. We're talking about getting the input from the command line. The next thing is that when you go to solve a program, solve the problem at Rosalind, and let me just pull up Rosalind again. You're going to be shown a sample data set like this, and you're going to write a program, and you see here that wow, 2014, that was when I first solved this. Eventually I got it correct. And so if I wanted to download this data set, it's going to be downloaded as a text file, and I'm going to put it into my downloads directory. And so if I look at that file, it's under my downloads and it's called Rosalind DNA. You see it's a much larger string. So that I don't have to take that string and paste it onto the command line, I'd like to write this program so that it will read the DNA either as a command line argument or from a file name if I give it a file name. So let me just show you real quick. If you've never written Python, you might be curious how to do that. And where you might do that. I'm actually going to put the code here inside getargs because I just feel like it's part of getting the arguments to the program. So I'm going to say if args.dna, which is that's where I'm going to find the argument for the DNA. I want to find out if that is a file. So there's a function called osPath.isFile, and that's going to return true or false if this thing is a file. So if that's a file, I'm going to set args.dna equal to opening args.dna and reading it. And then I'm going to rstrip, which will strip off any white space on the right-hand side. So strip from the right-hand side, that's rstrip. And I'm just going to overwrite what's on the left with what's on the right. So Python has a way of allowing you to do this because it's going to evaluate what's on the right-hand side of the equal sign. And once that's okay, it's then going to assign that to the left-hand side. So it's kind of weird that you can do this. In some languages wouldn't allow you to, but Python is fine to do this. And in doing that, now I can run DNA with something like that, or I can run it with the file that I just downloaded. Let's see. Oh, let's see. I must have done something wrong. Oh, I must not have saved it. Let's try that again. Oh, OS. OS is not defined. Okay, so good. It's not defined because I need to bring in that module. And so I go up here to import OS. And let me run that again. Okay, so that is the input either from the command line or from a text file. Are there any questions so far? So that bit of code this could have been put into the main function. I typically handle that in get args because it's just a common pattern that I use. Now I have a string of DNA and I need to count all the bases. So let me step back for a moment and start talking about testing. So I have written, let's see, where are all the files? There we go. Okay, so inside there's a tests directory, and you'll see that there are a bunch of input files, input 1. So if we look at that, it's a small text file that has just a few bases, 1A, 2 Cs, 3 Gs, 4 Ts. So if I were to run that, I would expect to see the output 1, 2, 3, 4, separated by spaces. Input 2 is a slightly longer one. That's the example string from the Roslyn page. And input 3 is just a much longer data set that I downloaded at some point. And I have also written this file called DNA_test.py. And let me just show you for a moment. If I run PyTest, just PyTest, this is what I see. And I encourage you to do this if you're following along. What's happening is that PyTest is going through the current directory and it's looking for any files that look like they might contain tests. So if the file name begins with test underscore or ends with _test, then it's going to look inside that file. Inside that file, it's going to look for functions that start with test underscore, and it's going to execute those as tests. And this first one tests that the program actually exists. So if we look at what PRG is here, up here at the top, I've defined that PRG, the program that I'm testing, is called DNA.py. And so it's just simply looking, does this program exist yet? Because the first step in all of these exercises is to actually create the program. And I always encourage the user to start them with new PY and get them running. So that's always the first step. Excuse me. And then the next one is that it actually runs your program with -h and --help. It's going to run the program and get the status of the program and the output. So I need to talk for a moment here about the status of a program. And this is very important in bioinformatics. Let me go to a command line again. And if I say echo hello, echo is a program that just simply echoes back whatever it's been given. So if I say echo hello, it will print hello to me. In addition, it signaled to the operating system its exit status. And I can see that in Bash by looking at the special variable ? Which is, it's kind of like saying, hey, how did that go? And I do that, and it reports the number 0 because weirdly enough, in systems programming, the output of 0 means basically 0 errors. So 0 is positive. That's thumbs up. It worked correctly. If I were to say, when I ran chmod without enough arguments, if I look at the exit status from that, you'll see it's not 0 because I didn't give chmod the correct arguments. And so it exited with an error value just to tell me that it wasn't okay. The fact that it's 1 is not necessarily indicative of any particular error. Sometimes programs will print, will use an exit status of 126 to mean database not found or something like that. Usually, it does the exit status doesn't mean anything at all other than the fact that it wasn't 0. So when a well-behaved command line program exits without problems, it should report 0. In any other situation, it should report not 0. So told you that because here I'm running the program with -h, and I'm looking at that return value and the output that it printed. And that comes from this function called get status output, which comes from this module called subprocess. So subprocess allows me to run other programs on my system and look at the output. Now, this in and of itself might be something that's really important for you to know in whatever kind of analyses you're doing, because a lot of times what we're doing is taking some program that someone else has written, trying to execute it with our data, and then, get the output of that, usually massage it to put it into some other little program that's going to do the next step. And that's an analysis pipeline. That's just, bread and butter for what we do. So if you were just wondering how in Python can I run some other program that exists on my machine, this is how you do it. In addition to running the program, you can also verify that the program exited with a 0 value by looking at the return value. So RV here means return value, and out is the output that was printed by the program. And I'm using this assert statement, which again, if you're coming from like C, that should look familiar. So assert wants its argument to be true. So I'm saying RV equal to 0. That is a way in Python of comparing two things for equality. So you've also seen here, the single equal sign is used for assignment. So the output from this is assigned to RV and out. Here, the equal is a way of saying, is it true that RV is the same as 0? So if this assertion fails, like for instance, because just the program wasn't syntactically correct, then the return value from trying to run it would be non-zero. And so this assertion would fail. In addition, I'm looking at the output. I'm going to lowercase it, and then I'm going to say, is it true that it starts with the word usage? And so if that runs correctly, then if both of these assertions pass for both of these flags, then this tests pass. And so what's happening here is PyTest is running each one of these. And crucially, it's running them in the order that they are defined in the file. So it starts with the first one, and then goes to the second one, then goes to the third one. And it's possible to have PyTest just stop testing as soon as it encounters a failing test, which is what I usually recommend people to do. And that's the flag -x to say stop testing. So for instance, if the file doesn't exist, then there's no point in trying to run any of the other tests. So if I run -x, it stops on this first F, which is the failing test. I also like to run it with verbose mode. And those are two short flags, and they can be given in any order. And they can also be squished together as -xv or -vx. It doesn't matter. But the V stands for verbose, and the X stands for stop on the first failing test. So when I do that, I get a little more output. And it's showing me here that it passed the first test, it passed the usage, it passed the dying on no arguments. So if we look at that function, it simply runs the program with no arguments. And it expects that now the return value is not 0. And this is really important because let me go back to the command line and show you. I can chain things together on the command line. So if I say like echo hello and echo world. So the double ampersand is a way of saying this and this thing, but only if the first thing is true. So it's like your truth tables in discrete structures. So if the first thing, if echo hello succeeds, then echo world will go forward. And if I go back and I say chmod and echo hello, the output of that is not the output from the failing chmod and then hello. The problem is that the chmod failed. And so the echo hello should never be executed. And that's exactly what happens. When I try to AND these things, the first thing is essentially false. So a false and a true is false. That's the way AND works. And so when you're chaining together programs on the command line, if you have a program that reports a non-zero exit value, then that should tell the whole thing to stop. And I have an appendix in the book on makefiles, and makefiles do the same thing. Makefiles are a way for you to describe a workflow, an analysis workflow, and built into that is that if one of the steps fails by reporting a non-zero exit value, then the whole workflow stops. And that's important because you need these things to fail when an input is bad or a disk fails or a database is not available. You're going to have to fix these problems manually and then restart your analysis. You would like to have some assurance that if the analysis actually completes, that all the steps in the middle were done correctly. Otherwise, you have to manually verify these things and then go back and rerun it, and that's no fun at all. So does that make sense about the exit value from a program and how that affects chaining it with other programs on the command line. Are there any questions about that?
There seems to be a question on the chat. Ryan is asking, is this command line behavior that you are describing fundamental to tests in CI/CD?
Yeah. So CI/CD, continuous integration, continuous development. Is that right, Ryan? Yes. So if you were, and Ryan and I were on briefly on a project together, and continuous deployment. Yeah. It's possible, like for instance in GitHub, which I introduced at the beginning. If you're working on a project with a lot of different developers, it's possible to have test suites to be run when people push code back to GitHub. And that is a way of continuously integrating people's changes into whatever analysis that you're trying to build, whatever you're trying to do as a team. And you want to continuously test that everything is working. And a lot of times in multi-developer projects, you're not allowed to integrate new code that doesn't have tests that verify that it does what it's supposed to do. And that's essentially what we're talking about here. And these tests are really incredibly crucial to writing programs that essentially don't suck, which is what we have mostly in bioinformatics nowadays. Just, software that was written by students and postdocs who were never given any training whatsoever in software development, who generally work on something for a couple of years and then leave to go, to their PhD program or to their next gig, and then nobody maintains these things. And that's just not the world we want to live in. So yes, this is fundamental command line behavior that you should understand, that was honestly never explained to me. And I just kind of figured this out, like, oh, like that's why that's really important. And it just makes a lot of sense. All right, so let me go back to this. So that is why here, when I run the program with no arguments, I expect that the return value should not be 0. And this is crucial. And that behavior is entirely handled for me by argparse. I don't have to run that. I describe to argparse that I require one argument. It must be the string. And if the user gives me anything other than that, argparse takes care of it, shuts down the script, reports a non-zero status, prints a nice useful error message, and I get all that behavior for free just by using the standard module. Okay, so essentially, for all the tests in the repository, if you use new PY to start your program and you get it to work correctly, you're going to pass the first 2 or 3 tests every single time, just simply because it's just verifying that your program is decently well behaved. Okay, so now we're getting to the part where it's dying on this test argument. This is failing, and the reason is because it is, let's look at the test itself. It's opening, there's a file and that has the DNA, and then there's some expected value. So these test 1, test 2, test 3, these are defined right here. They're tuples. We talked about tuples earlier. So if I run the program with this input file, I expect that the output should be 1, 2, 3, 4. Now this may seem like really simple. And I hope it does seem simple, because at its essence, testing is very simple. You run your program with known input and you verify that it creates known output. That's all there is to it. So if I give this input file, I expect this output. And what's going on here is that I have this file and this expected value. I'm putting this DNA, I'm opening that file and I'm reading it, which is the same code that I showed you just a bit ago. And I'm running the program with that as the argument from the command line. And I'm asserting first off that the return value from running that is 0, and that also the output from the program is what I expected. There any questions on that? So that's a test, and that's a really good test. Our program expects, DNA input and should print this output, and we just verified that. So what's going on here is that the output AC. It was the contents of the text file, ACC GGG TTTT, and that is what it's printing right now. And what it should have printed, what was expected, is 1, 2, 3, 4. So we need to go back over here, and instead of printing args.dna, we need to print the correct number of 1, 2, 3, 4. So that is the basis now for what we're trying to do. We're now trying to solve the test suite, and this is essentially, you may hear the term specs, so especially if you're working with a professional software developer, they'll say, well, I'm supposed to write this program. What are the specs? Well, these are the specs, the specifications. I give this input, I expect this output. So I'm going to go back to the text now, and let's talk about. And this is talking about all of that I was just explaining about the return value and what the tests mean and what they're doing. And so now let's talk about how do we iterate and count the characters in a string. So if you're new to Python, this may seem really weird. It certainly seemed weird to me. We can, well, the first thing is that I'm going to show you an extremely basic way of doing this. And then we're going to, once we solve the test suite, we're going to look at other ways to solve this. So the first thing that I can do is establish 4 variables that counts for A, C, G, and T. Now, there's a lot of different ways that I could have called these variables. Depending on your background, you might like to call it count uppercase A. Or maybe you start off with an uppercase character, or maybe you like to use all uppercase, which is actually the way I write bash for some reason. Or you might put an underscore there and then capitalize the A. There is, going back to the Zen of Python that's mentioned in the preface, Python programmers, as a rule, like for there to be one obvious way to do things. And there is a style guide for writing Python code. It's called PEP8. That stands for something Python, I can't remember. You can look it up. But they're numbered sequentially, and PEP8 is the style guide. And it says that function and variable names should be lowercase with words separated by underscores as necessary to improve readability. So that's what I use. And I feel like it's crucial. I write in a number of different languages, from Rust to Elm, and Python and Perl and Bash. And whatever language I'm using, I adopt the style of the community for writing that code. So where they like to put their braces and how they like to indent things and the way they name their variables, I go along with the flow, because when another Python programmer is reading my code, I don't want there to be any anything that throws them off. They'll be like, whoa, this is obviously a Java programmer, writing Python code. I don't want them to think that. I just want it to look like idiomatic Python. So I always stick with these naming conventions. So there's 2 different ways I could establish these 4 variables. I could write them all individually on individual lines, or I can use this version, which is basically creating 4 tuples on each side. I'm creating a 4 tuple on the right side and then assigning it to 4 values on the left side, which is a pretty convenient way to do this. So I'm going to take that code and I'm going to paste it here. So I just created 4 variables, count A, C, G, and T, and initialize them to 0. And again, in Python, we have to initialize a variable in order to use it. You can't just declare a variable and it be kind of undefined value. So now that we have these initialized, I can now iterate over the characters in DNA. In some languages, DNA is a string, and there would be some sort of a method that you would call to get the characters out of it. That when I came to Python, that's exactly what I was used to doing in Perl, and I was looking for that. And then I found that the idiomatic way in Python to do this is to use a for loop. And I'll call it, I could call the variable that's going to hold each base, I could call it whatever I want. I could call it char for character. I'm going to call it base because that's what it is. For base in args.dna. And then I'm just going to print that. Let me fix this for a second. And I'm going to print the base. And then I want to talk about a couple things about Python syntax that may be new to you. So each character in args.dna is going to be put into base. And then this colon, the colon at the end, is a way of in other languages that use curly brackets, you would put the block in curly brackets that follows this for loop. In Python, you introduce a block with semicolons, and you're letting the compiler know that what follows is a block of code, and the way to indicate that block of code is by indentation. It's if you're going to indent with tabs, you're a fundamentally bad person, but you must do it consistently and use tabs everywhere. The morally upright way to indent code is with spaces only, and typically it's 4 spaces. It's possible to indent with only 1 or 2 or 3 as long as you're consistent, but you would then be again in moral turpitude. So indent only with 4 spaces, and in all the block, everything that's indented to the same level is at the same is in the same block. That's crucial to Python. Some people hate white space dependent languages, and some people love them. The thing that I would say is that it's fine because I almost never manually format my code. I use code formatters that do this for me, and I just simply let them format however it wants to do it. There are 2 of them that are very popular. One's called Black. It takes its name from Henry Ford, who said that you could have a Model T in any color as long as it's black. So you basically get very little choice over how Black will format your code. And the one that I tend to use is YAPF, which is yet another Python formatter, which came out of Google. For a long time, Google, Python was one of their main languages. They've since replaced that with a language called Go that they created for themselves. So this is how I'm going to iterate over this. And if there's no point in running the test suite right now, I know this is going to fail. It's not doing the right thing. So instead, I'm just going to run the program with like ACGT. And what I verify is that it is printing each of the bases. And I can double check that with, the tests input, what did I call it? Input 1. And if I use it with an input file, it doesn't matter. It's reading the DNA from 2 different sources and it's iterating over it. So are there any questions so far? So, what I'm stressing here is essentially how to create new variables and how to iterate over characters in a string. Helpers, let me know if there are any chat because I can't see that. Okay, thank you. And the for loop is really used a ton in Python, which is very different, as I understand, from R. R is a much more vectorized based language, and in fact, for loops are pretty notoriously slow, as I understand. Oh, actually, I can see the chat. Why can I see that now? Okay, cool. Okay, in this example, indenting print will return different results. And yes, because if I don't indent the print, then it's not, then it's no longer it's at the same level as the for, so it's not actually belonging to the block of the for loop. So crucial that you get this right. And if I indented 2 spaces, actually, let's just see what the result is. Oh, okay, that seems to be okay with that. I'm still going to make it 4. So what was I just saying? Oh, we're just trying to, I was going to say about for loops. I understand that R tends to not use for loops a lot, whereas they're extremely used in Python. And you can use for loops over anything that is in a sequence. So the characters in a string are items in a sequence. Elements in a list, I showed that earlier. I showed named tuples. That's another kind of list. You can iterate over each of the values in a tuple. You could iterate over all the lines in a file. You could iterate over all the records returned by an SQL query. So for loops are just used in a ton of places. So that's how we iterate. Now the question is, we need to count the bases now. So the goal is not to print them, but is to count them. So how can we do that? I'm going to create basically a decision tree. I'm going to say if base is equal to A, then, and I say that with a colon. And again, so I'm now creating another level. When I hit enter in VS Code, it automatically indents because of the colon. It sees, oh, you must want a new block of code. And so I'm going to make count A go up by 1. So I could say that count A is equal to count A plus 1. And that's one way to do this. But we do this sort of thing so often that there's actually a special operator for doing that. And it's the plus equal operator. And probably most of you have seen this from other languages. If there's any question about that, what's happening is that count A is going to go up by the value that's on the right-hand side. So I'm adding 1 to it. If you come from C++ or C, you might be used to the unary operator plus plus, which can go sometimes before or after. I know Perl did this. Python does not have the plus plus operator. There are very few unary operators. So it's plus equal 1. So I have to handle this for all of the other ones. And the way that we spell else if in Python is elif. So elif base is equal to C. Then I want count at C to go up by 1. And I just have to do this for all 4 bases. Base is equal to G. Count G plus equal to 1. Woo. And I'm gonna say elif to if I said else count T goes up by 1, then it could be any other character. And so I really want to make sure that the base is actually equal to T. So count of T is plus equal to 1. And that is it. And you notice, so without having brackets, it's one of the things I kind of don't like about white space dependent languages is I can't jump to like the other bracket, the matching bracket to get to the end of a block of code. But that's how I essentially enter those blocks into Python. Are there any questions about how I typed that, the syntax for that? So finally, we actually should have a working program now. If I say, I'm going to show you one way to print the results. I'm going to say print that. So print can take more than one argument and will by default, you put a space in between each of those values. So if I run this now, it prints 1, 1, 1, 1. Let me run it with the input file. It prints 1, 2, 3, 4. This looks promising. This should pass my test suite. So I can say pytest, pytest-xv. Yay. That is a fully passing test suite. And so to an extent, we're done. You just learned test-driven development, and that's cool. And hopefully you learned a few things about Python and command line programs and things like that. But really, that's just the first step. Like we now have a working program. We know one way to count all the bases. I actually, if you look over here, have 7 different ways to count them. And so, and the point of exploring all these other ways is to see what else we can do with Python, because this is an extremely verbose solution that's very, very much like you would write something in C. But there are a lot shorter ways to write this in Python that use some things that are unique to the language. So I'm going to take a moment here to see if there are any questions about what I've done so far, because I don't want to go forward unless you're cool with this. Yes, so someone is pointing out that R is not white space dependent. And oh my God, can I tell? Because I've had to look at some R code where people just don't put spaces. You can put spaces is where you want or not put them. And it just, I mean, people talk about Perl being unreadable. I've seen some R that is just it's unfathomable. And the nice thing though, there's hope. There are formatters. In fact, I think one of the programs is called formatter, right? And they like in R, they like to just put R on the end of things, dplyr and things like that. So there's formatter. I think I've looked at a couple. There's also a way to create command line programs in R that validate command line arguments, just like very, very similar to argparse. Not quite as nice. And on the program that I was working, yes, Ryan points out lintar. Linter works pretty nice. And really, really important, I think, if you're working, even if you're just working by yourself, you should use these tools to format your code because it will make it more readable, make it easier to maintain your code, to share it with other people. If you're working on a project with other people, there are these things that we call religious wars in programming, like Vim versus Emacs. There's no right answer. I use Vim. I've used it for like 20 years. I love it. But if you prefer using Emacs, who cares? As long as you get the job done. When it comes down to formatting code, like do you cuddle your braces or do you put them on the other line? Who wants to fight a war about that? Let's just use a formatter that will format everyone's code the same way and just get used to it. And so I highly encourage you to adopt formatting stuff, to adopt standard modules like argparse to do these things, because there's a lot more important things to worry about. Okay, so I'm gonna take this example and I'm gonna go back to the book for a moment. So we go through here. This is how, I point out, this is how I'm printing this version. I'm pointing out that this is controlled by this argument called sep. So if I wanted to put double colons in between them, I would just say sep equals double colon. So if you want to alter this behavior with print, this is how you do it. There's also an end variable. And so here you can put, -30 dash. I was on my high school newspaper, if you can't tell. So if you want to know more about these kinds of functions, go into your REPL. I think this is one of the best things about the REPL. And you can say help print, and it will show you the documentation for the print function. And those things are all spelled out right here. So here's the separator, here's the end. There's another one called flush and something called file, which I explain later in the book as well. So a lot of really great documentation available to you inside the REPL. Okay. The next thing is I want to go a little farther with the testing. So far we've just been running the tests that are in that DNA test.py. But there's other tests that we can incorporate too that verify that our program is linted correctly and that our types are being run properly too. And so I mentioned this in the requirements document that I talked about at the beginning. These should have all been installed for you. In addition to PyLint and Flake8, there's the way to integrate them into PyTest. So PyTest, PyLint. And if I run, so this is what I've been running so far is pytest.xv. If I've installed the PyLint and Flake8 and MyPy extensions, I can actually run it like this, and it will incorporate extra tests for me, basically ones that it creates on the fly. So notice here, there's 5 tests. Here I'm going to run, and it's going to create a couple of extra tests. It ran Flake8 here and it skipped because it just didn't find anything to check. MyPy ran and passed. And so it essentially created 2 new tests for me to make sure that my program was formatted correctly and that I was using my types correctly. That is really, really helpful. And but that's a lot to type every time you want to type it, every time you want to run the test. So I have created something I've added in every single directory. There's something called a make file. And I have a whole appendix. The first appendix in the book spends a few pages trying to explain what make is and what a make file does. But essentially, it's a way of creating a little shortcut. When I run make in this directory, and I give it and I say make test, it's going to look for the existence of a file called makefile, either uppercase or lowercase. And it's going to see this thing called a target or a recipe. That needs to be flush left, and it ends with a colon. And then all the commands that it executes must be indented with a tab. Absolute requirement has to be a tab. The story I was told is that the guy who created this, he realized that he really would prefer it to be spaces, but at that point he already had 4 users and he didn't want to break their experience. So he kept it with tabs. Make has been around since 1976. So not quite as old as me. So if I say make test, it's going to run this command, which is actually, quite a bit. So I run make test and it runs all that for me. And it actually found a few other things, like it says, hey, you're importing text IO, but it's not being used. It says there's too many blank lines. I mean, it's pretty snippy about it. So, okay, if I go get rid of text IO, I'm bringing in some code I don't need. If if I go run make test again, it's still complaining about like some blank lines. And normally if I was working in VI, I would just put this through a code formatter and it would fix those things. But those are good things to check repeatedly as you're developing. You want to verify that, you know, your code is formatted and all those kinds of things. So a make file is basically a way to create a shortcut. They can do a lot more than that. And I really encourage you to read about them. The next thing, I won't have time to go over all these, but the next thing I'd like to show you is how to create a unit test. So I want to take the code. So what I've been showing you so far are what are called integration tests. So I have written these tests for you. They run the program from the outside the way your users will run it, and they verify your program does what it's supposed to do. As you're developing code, you're going to want to write small functions that do a very limited number of things. Usually one is good. And then you want to write a test to verify that that function does what it's supposed to do. So for instance, I can't remember what I called it in the book, but all of this code right here belongs in a function. And in Python, I can create a function by using the function called def. And I'll just call it count. And for the moment, I'm just going to paste this code. So this is all the code that I just was executing. And actually, you know what? Let me stop this for a second. I'm going to go back to the way it was. Okay, let me start over. I'm going to create a function called def count. It's going to take some DNA that's a string, and it's going to return a tuple that is an int, an int, an int, and an int. And I'm going to put a doc string, count DNA. And for the moment, I'm going to return 0, 0, 0, 0. Okay, so what I've done here is I've essentially made myself think about what this function is going to take and what it's going to return. This is getting a little squiggly line because it doesn't know where tuple is. I need to import tuple. This is a type. Okay. And I want to write a test for this thing. And in order to run it with PyTest, I need to call it test underscore something. So I'm going to call it test underscore count. The function is not going to take any arguments and it's not going to return anything. So technically it returns none. And I'm going to say this is going to test the count function. That's the doc string. And I'm going to assert that if I count the empty string, for instance, that it's going to return 0, 0, 0, 0. That is test-driven development. So I've thought about a function that I want to write, and I write a test for it. And what's interesting is that I can run PyTest on this dna.py, and what it does is it looks inside. Let me run it verbosely -v. It looks inside the dna.py program, finds the function called test count, and runs it. And right now I'm passing count an empty string and I'm expecting to get back 0, 0, 0, 0. And that works because that's the only thing the function does, right? But I also want to verify, for instance, you know, if, whoops, that if I pass it the single string A, then it should return 1 in the first position. What is it? So let me, interesting. What is happening? Okay, let me run PyTest on that. XV. Now it's not working correctly because I'm passing it this value and I'm expecting to get back 1 and it's always returning 0, 0, 0, 0. Just to make that look nicer, I'm going to put that in parentheses. So essentially, I just need to take all of this code and move it into my function. So this is something I don't like about IDEs. Don't like using the mouse. I'm going to paste my code in here, and now I'm going to return those counts. And now if I run this code, oh, sorry. Let's see, in arg, I'm still referencing args.dna. For the moment, I need to comment this out because that's not syntactically correct. Okay, now my function passes. So I just took all the code from main and I stuck it in a function now called count that takes DNA as an argument, that must be a string, and it's going to return a tuple that has 4 integer values in it. And that's how I describe this using types. And I've moved all this code here. I've written, one assertion, and actually there's a bunch here. I'm just going to go over here to the unit, and I'm just going to take all of these. These are some other assertions that I can paste in. Whoops. And so if I run with the string 1, 2, 3, XYZ, I expect to get all zeros back because there's no DNA nucleotides. I'm checking here that if I just give one nucleotide, it puts it into the correct position. And here I've got, this string where there's 1, 2, 3, and 4 of the different things. And if I run this, it passes. That's the basis of test-driven development. So you're going to write a function and you're going to write a test for it. And now I can go back here and get, for instance, I'll change the main code. I'm going to count args.dna, and then I'll print that value. So if I make test, it's still unhappy about some blank lines and stuff. Let's just do PyTest. The functions, the program still works. It should still work. I mean, I haven't really changed fundamentally how the program works. I just moved some code around. But the point about this is that I'm refactoring my code. So the way I'm refactoring my code at the moment is I'm just organizing it better. For such a short program that does just one thing, this seems like overkill. But a short program becomes a long program, becomes a much longer program. And typically I like to have a function only be 50 lines of code or less. Like I would like for it to be able to fit in, like, say, this amount of window. And if I have a function that goes on for hundreds and hundreds of lines, it's too long. It needs to be broken up into many smaller functions, hopefully each of which will do just one thing. For instance, this function counts a string of DNA, returns a tuple, and I can write a test for it, and I can verify that this function works. And if I go, change something, like let's say I accidentally typed that wrong. If I go run this, my test suite no longer passes, because it tells me right there when I ran it with this value, I expected 1, 2, 3, 4, and I got 1, 2, 3, 0. And so that's the kind of assurances that you start to get from test-driven development. I think that I'm about out of time. I can't see my clock, actually. No, I've got a few minutes left. Okay, so are there any questions with that? Because now I'd like to show you just a couple of ways to write this much cooler. Okay, I'm just going to check. Nothing in the chat? Okay. All right, so it turns out this is a really long way to write this. There's a much shorter way to write all of this code. I'm going to... Again, I do not like using a mouse. I think that I can do, there's an option here for commenting out, but I'm just going to delete this code for the moment because it's all in another function that, in these other programs that you can look at. It turns out that there is, I can return, and so this is also crucial to Python. Some programming languages will simply return the last evaluation, the last statement, the last expression from a function automatically, but Python will not. You must use the return statement, or otherwise it will return none. by default. So if you don't have a return statement in your function, the function does return something. It just returns the value none, which is written like that. It turns out I can do args dot, I'm sorry, not args, but DNA dot count A. So that what this will do, and it could be helpful to look at it in the REPL here. Let's say the DNA is equal to ACTG, or how about AAC? If I say DNA dot count the letter A, it finds 4. It's also interesting if I say count AA, it finds 2. So it finds a substring, and they're not overlapping substrings. So basically the count will look for how many times one string occurs inside another. So that one string can be a single base, a single character, or it could be some longer string. And what's nice about this is that it's safe to use, like if I try to count the T's, there are no T's and it returns 0. So I can therefore write this as count DNA, count A, count C, DNA, count G, G, and DNA, count T. And this is what is nice about testing. If I run this, I verify that my program still works. And that's the point of writing functions, is that once the function accepts some values, returns some values. What goes on inside is completely, it's a black box. You shouldn't know or care what goes on inside a function. And so it allows me to have a test. The test doesn't care how the function is written. The test only cares, I give you this, you give me this. And I've read about, young British children being taught this please and thank you game. So you don't get the cookie until you say please. And then when I give it to you, you say thank you. There's the expectation, please and thank you. So that's our expectation here. I give you the empty string, you give me back 4 zeros. I give you back the letter A, you give me back 1 and 3 zeros. So it doesn't matter how I implement this. And all of a sudden I've gone from, what was that, probably 10 lines of code down to 1 line of code. And there's actually even shorter ways to solve this. And I'll let you, I don't have time to go into like dictionaries, default dictionaries, but I'll just show you here this last version uses something called a counter, which is a way of creating a bag or a multi-set. And so I can show you from the command line, if I import from the collections module, I have to say, sorry, from collections, import something called counter. What's cool is I can say, make a counter of the string AC, and it returns a dictionary that says, I found A 3 times, G 2 times, C 1 time, T 1 time. And so those are the kinds of modules that exist in Python. There's many, many more to learn about. I'm going to stop sharing here, and I'm just going to look for if there are any comments. Yeah, I just want to, and I'll, that's essentially what I wanted to show you. So I have a whole book about this. You're welcome to read it for free. You can get it from the U of A library. You're welcome to share it with your lab mates. I'm probably going to be using this, some of that material as well, a lot of that material in the BE 434. So if you or anyone you know in your lab would like to learn more about how to write Python programs for doing data analysis, it is being printed right now. It actually went to the printer about a week and a half ago. So you could order it from Amazon and get, I'm sorry to say it's $90. I didn't get to set the price, O'Reilly did. But if you want the dead tree version, you can order it from Amazon, or you can read it for free in the electronic version on the library site. And so, yeah, I have a lot more to say about like how to write Python effectively. But the ideas that I've covered are applicable to any language that you use. So again, Brian and I were on a project last summer. It was R-based, and I was trying to introduce the idea of test-driven development in this project that was entirely based on R. It did not go well, but these ideas can be used with any, and they are used industry-wide. And there's no reason why test-driven development should not be taught to beginners from the beginning, and used as a teaching tool, and also just for you to understand your code better. I think that if you were to adopt these techniques, again, no matter the programming language that you're working on, I think you'll find that you understand your code better and are able to write programs faster that work that can be refactored and expanded. So anyway, that's all my time. And if you have any questions, I'm happy to read them in the chat. So I put into the subject page, you can reach me at kyclark@arizona.edu. My personal address is kyclark@gmail.com, kyclark@c-path.org. And so you can reach out to me if you have any questions. And I'm happy to, if you wanted me to come and just talk to your lab group about these kinds of ideas, to introduce the book, to introduce these, or just to chat about how to write code more effectively, I'd be happy to do that. All right, that's all my time, and I hope you enjoy the rest of ResBaz.
All right, thank you, Ken. I'm gonna stop recording now.